this concept is very important. So I want to give you the background of this concept. Right. Differential. Review the differential concept. Yeah. First, let's look at what's the definition of differential. The term differential is used non-rigorously. Yeah. At the beginning, non-rigorously. The current concept differential, it is rigorous. Yeah. But at the early time of calculus development, non-rigorous. Why non-rigorous? Let me explain it. Because early time there is a special concept called infinitesimal. Infinitesimal. Mathematicians introduced this special concept in development of calculus. The meaning is infinitely small. Infinitely small. Small. Okay? But make it infinitely small. So what's that? Infinitely small. Infinitely small, but it cannot be zero. Infinitely small, if you treat it as zero, it's wrong. So it is a non-zero quantity. Cannot be zero. But infinitely small, what's that? Think about that. Yeah. Cannot be zero. If it's zero, that's conceptually wrong. Fundamentally wrong. You cannot make it zero. Yeah. But infinitely small. Then many mathematicians, they cannot accept this special concept. How can you get some concrete quantity that is infinitely small, but it's non-zero? How can you get that? So most of the mathematicians at that time, they had hard time to understand this concept. That's the reason they treat this differential non-rigorous. Because if you do not accept this infinitesimal concept, then you cannot treat differential as a rigorous concept. Yeah. So then, many mathematicians try very hard, many different ways, try to make the whole theory, the calculus theory, whole theory, rigorous. Yeah. Try all different methods, try to make it very rigorous, after hundreds of years development to make it rigorous. Yeah. Not easy. Yeah. All right. So before the limit concept was, because at that time, there was no limit concept. At that time, before the limit concept was introduced. Yeah. So limit concept is critical for the calculus development. Yeah. All right. So they need to create this limit concept. Yeah. To fix many holes in calculus theory. That limit concept is critical. Yeah. All right, so here let's understand the infinitesimal concept. Yeah. All right. Infinitesimal quantities played significant role in the development of calculus. Yeah. But before the limit concept was introduced, it is not rigorous. Yeah. How can you get something infinitely small but non-zero, right? A contradiction. So it's a contradiction. So you cannot, take it. Yeah. Yeah. All right. So if x is a variable, dx denotes infinitesimal change in the variable x. Yeah. So because the differential dx relies on this infinitesimal concept, infinitesimal change in the variable x. The small change, yeah, but if you use some concrete small amount, not good enough. because concrete small amount, it's not infinitely small, right? It's not infinitely small. So you need to use infinitely small amount. How can you do it? Okay? Yeah. But you can only use your imagination, yeah, conceptually, infinitely small. Yeah. All right? Yeah. The use of differentials in this form, a lot of criticism, attracted much criticism. Yeah. Most mathematicians couldn't accept it, this explanation. Yeah. Contradiction. Big contradiction. Yeah. So the theory, yeah, because a lot of holes should be filled. Yeah. Important improvement. Yeah. All right. After the development of epsilon delta, yeah. So that theoretical. Yeah. So how to describe the limit? Yeah. So those mathematicians, they create the epsilon delta language to give rigorous definition of the limit continuity, because continuity relies on the limit concept. Now, the first concept is the limit concept using the epsilon delta language. Yeah. So here I do not repeat in calculus. So you have that rigorous definition of limit. Okay? Epsilon delta. Yeah. That is rigorous. Yeah. That concept. All mathematicians at that time, so they agreed, oh, this definition is very rigorous to define the limit. Yeah. No argument. Yeah. So that's moving forward, step by step. Yeah. All right. So that the notion dx gave a solid conceptual foundation. Yeah. Because after you have the limit, yeah, that is important. Yeah. So then those mathematicians gradually accept the notion differential dx. Yeah. Because there is a rigorous foundation limit there. Yeah. So based on the understanding of the limit. Okay? Yeah. But still very abstract, even with the limit. Because limit comparing with infinitesimal. Yeah. Infinitesimal is not rigorous. Okay? Yeah. So now mathematicians, current mathematicians, they never use infinitesimal concept. Not rigorous. Yeah. But they use limit concept. Yeah. All right. Yeah. Yeah. So now the differential concept is established on top of the limit concept. Now we treat it as rigorous. Yeah. But when we talk about it, so you need to use your imagination. Yeah. Because it's still a very abstract. dt, you should understand. So this concept, first, it cannot be zero. Yeah. dt is a non-zero concept. Non-zero. Okay? Yeah, first. Second, it is very small. So actually, the same meaning of infinitesimal. But we don't want to use infinitesimal, this word. We don't want to use this keyword. No. Never use infinitesimal directly. Yeah. But conceptually, the same thing. Yeah. Infinitely small, non-zero. That's the two properties of differential. Yeah. All right. Yeah. Recall definition of derivatives. Yeah. We try to connect between derivatives. You have no problem, right? Definition of derivatives. So that's dx over dt, the limit. Delta y over delta t, where delta x not goes to zero. Yeah, that's the definition of the derivative. Yeah. But in this definition, you can already see the differential. Okay, dy over dx. Yeah, the differential. The ratio of two differentials. That's the derivative. Yeah. All right? Yeah. So now we take the view, yeah, because we can separate. Yeah. In calculus, at early time, we do not separate, right? Yeah. So we treat this ratio, the whole thing, as one concept, derivative concept. We do not separate them. Yeah. But here we need to separate them. Yeah. All right. So when delta x approaches 0, delta y approaches to dy. Okay? Yeah. dy. Yeah. We do not want to. So here, there is one little subtle step. We do not want to say delta y approaches to 0. If delta y approaches to 0, then we cannot study anything, right? So everything is gone. Okay? We have nothing to study. But here, if you make a delta y approach to dy, yeah, differential. We have something. We have some non-zero quantity we can study. So we can develop a lot of meaningful things. Yeah. So here it's important. We use differential. Yeah. When delta x, delta y approach to 0, yeah, we use differential. Yeah. So we have many formulas we can study, we can manipulate. Otherwise, nothing. If you use 0, nothing. Yeah. So, because with the limit concept, here we want to imagine. Yeah. Yeah. Because, so here, the harder part is the x, because understand these two quantities, non-zero quantities, it is very abstract. Yeah, very abstract. Yeah. But here, we need to pass that step. Yeah. The jump, pass that step. Non-zero step. Okay? Non-zero step. Yeah. So very small but non-zero. Yeah. Because their ratio is non-zero. Yeah. Ratio. Yeah. The derivative in general, non-zero. Okay? Special situation, it could be 0, but the general case, non-zero. Yeah. The ratio non-zero, then we want to imagine the ratio of two non-zero quantities to be non-zero. That's natural, right? Yeah. dy over dx, two non-zero quantities. The ratio of them non-zero. So we have no problem to treat the numerator, denominator non-zero, right? Yeah. Yeah. All right. So now the relationship. We can write dy equals the derivative times dx. Because here, there is a cancellation, right? After cancellation, both sides are the same. Yeah. But we intentionally, we write this form. So dy over dx, this is a derivative concept. So we use derivative. Yeah, here, now let's use y prime to represent derivative. So the relationship between dy and dx is a derivative multiple of dx differential. Now, that's the relationship between two concepts, dy, dx. All right? That's the basic understanding, yeah, initial understanding of the differentials. Yeah. But it's important. Yeah. All right. Because later we will use differential concept to do a lot of discussion. Yeah. So we need to really pass the understanding stage of this concept. Yeah. Otherwise, later you will feel harder and harder to understand many methods. Yeah. All right. Yeah. Instantaneous rate of change. Yeah. Because y prime is a function of x variable. Yeah. Instantaneous. Yeah. Yeah. Because the variable x keeps changing. Yeah. Yeah. When we calculate the derivative, we need to know at which x we calculate. So that's the instantaneous rate of change. Yeah. All right. Yeah. So that's the basic. Yeah. The remaining slides we did it last time. So now let me jump to next topic. All right. The next topic we have another word problem number 6. Yeah. Let's do this one. Yeah. Leaking tank. Yeah. Let's solve another word problem. Leaking tank. Yeah. All right. First, let me give you the question. Yeah. Look at this tank containing water. Yeah. So it's not a brine, salt. Yeah. Water this time. Yeah. All right. The question. It concerns outflow of water from the cylindrical tank with a hole. Bottom, there is a hole. Okay? Yeah. Flow out, water. Yeah. Out. Hole at the bottom. Yeah. You are asked to find the height of the water in the tank at any time if the tank has diameter 2 meters. The height function. Okay? Yeah. Little h of t. It's a function of t, time t. Okay, yeah. So you need to find this function, h of t. Okay, all right. The hole has diameter 1 centimeter. Yeah. 1 centimeter, the diameter of this hole. Yeah. All right. And the initial height of the water when the hole is opened is 2.25 meters. That means at the time t equals 0. Yeah. So our initial, that's our t0 time. Yeah. So this time is 0. T equals 0. Yeah. So the height is this 2.25 meters. Yeah. All right. Then the question. When will the tank be empty? At what time? You need to find the specific time. At what time the whole tank becomes empty? That's the question. Okay? Yeah. We need to solve this problem. Yeah. Okay. Yeah. All right. So now we need to do analysis. Yeah. Modeling, right? Yeah. So our, standard procedure. Yeah. All right. Modeling. We need a physical law, some physical law. Yeah. All right. Torricelli's law. Yeah. Torricelli's law. Okay. Yeah. An Italian mathematician. Yeah. Torricelli's law. Okay. All right. V of t. V velocity. What's the V? Because when the water flows out from the bottom, there is a velocity, right? How fast the water flows out? Velocity function. It is a function of t. So this physical law tells us the velocity function equals 0.6 times root of 2 times g. You know g, right? Yeah. Yeah. Acceleration of gravity, right? Yeah. The gravity constant. That h function. Acceleration of gravity at the surface of the Earth. Yeah. So two different ways to write. 980 centimeter per second squared. Okay? Yeah. Or 32.17 feet per second squared. Yeah. Here, you can see the unit. We used meter, centimeter. So we should use the first version, right? Yeah. More friendly. Yeah. All right. Yeah, but sorry. Now we need to set up equation. Now, first thing, you can see the units, meter and centimeter, two different units. Now, we should convert to one, right? Yeah. Yeah. Which one you feel better? There are two ways. Yeah. When we do conversion, first way we can convert it to all centimeters. Another way, all meters. Which way you like to take? You'll feel more comfortable. All meters. So all you agree? Anyone? Oh, yeah. But yeah. I also prefer meters. Yeah. But our textbook uses centimeters. Yeah. Yeah. Why? Yeah, I don't know. The author's preference. Yeah. Yeah. But here it looks meters easier, right? Yeah. All right. So let's use the easier way. What is the relationship between V of t and H prime of t? So here, if we only use this Torricelli's law, you have V function, you have H function. V function is unknown, H function also unknown. You have two unknown functions, but only one equation. How can you solve it? How can you solve two unknown functions from one equation? Impossible, right? Yeah. Yeah. Nobody can solve it. Sorry. That means we need to find another equation. Another equation between V function and H prime, the rate of change of H, rate of change of the height function. Can you find the relationship, the V function and the rate of change of the H function? Yeah. That's the some hidden relationship. You need to discover some hidden relationship. Yeah. All right. Based on your observation. Yeah. But here you can see, when the water flows out, the volume of the water in the tank changes, right? The volume changes. Yeah. Think about the amount of volume reduced. Yeah. The amount of volume of water is decreasing. That amount, the reduced amount of water, is it the same as the amount of water flows out? Yeah. Yeah. Same amount. Amount of water reduced inside the tank. Inside tank. If you can measure amount of water inside the tank, right? The volume. How much is the volume? You can measure that. Yeah. Yeah. It is reducing. It is decreasing. Yeah. The decreasing amount equals the amount of water flows out. That's the relationship. That if you can observe that relationship, you get another equation. That's the second equation we need. Yeah. All right. Volume change equals the volume of the water outflowed. That's the second relationship we need to use for our second equation between V function and H function. All right. Now, we need to how do you represent volume change? Left-hand side quantity. How do you represent right-hand side function? Volume of the water outflow. Yeah. Let's represent them one by one. Yeah. Left-hand side quantity. Volume change. Volume change. Volume, V function, right? Yeah. Can you represent the V function inside the tank? V function. Volume of the cylindrical water body. Can you represent it? Yeah. It's easy. Yeah. But volume change. You need to represent the change. Not the original volume part, the change part. You want to represent the change part. Okay? Yeah. Conceptually, the change part is, yeah, all right, yeah. Before we do represent, notation. Capital D equals diameter 2 meters, D. So the radius 1 meter. Yeah. In our calculation, we like to use the radius-based formula. Yeah. Diameter, yeah. If you want to use diameter, also okay. But yeah. But radius, yeah. Here we use the capital R. Yeah. That big radius. There is another radius. Little d, diameter of the bottom hole, 1 centimeter. Yeah. We want to convert it to meter. Yeah. So the little r radius equals 0.005 meter. Conversion? Yeah. Yeah. All right. Pretty small. Yeah. But whatever it is, we just use it. Yeah. All right. Now we are ready to represent these two quantities. All right. Left-hand side, volume change, conceptually, it's a delta V, right? Yeah. What is delta V? That's the next step. First, high-level overview, delta V. Volume change. Yeah. But you need to write explicit formula for delta V, right? Yeah. You need to write explicit formula. That difference in volume. Cylindrical shape, right? Yeah. Think about it. After a certain amount of time, the volume of the water body inside the tank changes with certain height difference. There is a height difference, right? Yeah. All right. Equals pi capital R square, yeah? The area of the base of the tank, right? Yeah. The base. Yeah. Yeah. All right. Times delta H. That's the specific representation of the delta V. Okay? Yeah. Left-hand side. We complete the left-hand side. Then, right-hand side. Right-hand side, we need to focus on the outflowing part. How much water outflow from the tank? How to represent it? Okay? Yeah. All right. Decrease. Pay attention. The volume decreases. Yeah. Here, I put this information here because it will tell us the sign. When you determine this quantity, we use the positive or negative. No. There is a sign issue. Yeah. Decreasing the change amount change is negative amount. Okay? Reduction. How do you represent reduction? Not increasing. Negative. Okay? So the sign is important. All right. Then right-hand side. So now you focus on this little hole at the bottom. The area of this little hole, pi little r square. Pi little r square. Okay? Yeah. Then You look at the outflow. Outflow, there is a time period you need to consider, right? There is a certain time period. Water is outflowed, certain time period. What's that period? We use delta T. In that small amount time period, delta T, we assume the flow out velocity, V function, your flow out velocity is V times the time period delta T, then you time the base area pi little r squared. Is that volume? Is that the volume flow out? Can you imagine? Use your intuition. Use your intuition. Yeah. Is that hard to imagine? You can draw a diagram if you feel hard to. All right. The base of that little hole. Okay? All right. Water flows out in certain velocity. There is a velocity, V, velocity. Okay? Travel, you can think about it. Water travel in some little time period. The traveling period of time, delta T. How long does it travel? How long does it travel? V delta T, right? Yeah. The height. What is the height of this little cylindrical shape? V delta T is the height. What is the volume? The base area times height, right? Yeah. So this is height. Height. Okay? Height. So base times height, the volume of that little cylindrical shape. Okay? Yeah. You need to, based on your intuition, you need to figure out that formula. Okay? Yeah. So that's so for our most of our word problems, you really need to get into the, understanding the details of the question. Yeah. All right. So here you need to use your imagination, intuition to figure out the formula representation. Yeah. That's an important step. Yeah. All right. Now we have, this is our second equation. Okay? This is our second equation. Now we need to write a friendly version of the second equation. Now, this delta T, delta Y, still not quite friendly. Okay? Yeah. That's our initial rough formula. Because when you use delta V, delta T, it is approximation. That's not a precise representation. It's approximation. Why I say approximation? All right. Look at here. The time period, the length of the time period is delta T. During that time period, when you use this velocity function V, V keeps changing in that time period, right? Yeah. V function, the value of V function keeps changing in that time period. It's not a constant, right? The V function, it's not a constant. Yeah. So that's why when we do this representation, it is approximation. It's not an accurate representation. It is an approximate expression. Okay? Yeah. But how do we make it exact? Yeah. Because when we solve equations, we want to solve exact equation, not a rough approximate equation. Yeah. Okay? Yeah. To make it exact, from approximation to exact, we take a limit. When delta T goes to 0, think about it. we make this time period very small, goes to 0. Can you treat V as constant? When delta t approaches to 0, becomes smaller, 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 take limit. Then because your time period becomes smaller and smaller, goes to 0. So the change of velocity similar to constant, right? Yeah. Because the time period is too short. And you consider limit. So here the limit is important. Limit goes to 0 with infinite small amount. Infinite small amount. Here you need to use that concept. Infinite small constant. Then V becomes constant. In that infinite small time period interval, V becomes constant. Yeah. Then, when you take the limit, this approximate formula becomes more and more accurate. At the end, what is the end state? End. Because you take the limit, the delta t becomes dt. It's the limit state. In that state, the formula is exact. No approximation. It is an exact expression. No approximation. After the limit process, it becomes exact. That's the power of differentials. We get accurate expression. We start from approximate expression. Then, after we take the limit, we get exact expression. That's the power of differentials. Okay, all right, yeah. Try to get used to this kind of thinking. Yeah, this kind of thinking. Yeah, very abstract. Yeah, but we need to be able to do this kind of logical reasoning. Yeah. All right. Now, let's take the ratio, but when you do it, don't forget, because the height number decreasing, so we should use negative sign to represent the decreasing information. Yeah? Changes in the negative direction, not positive direction. Yeah. Negative direction. It becomes smaller and smaller. Okay? Yeah. So otherwise, you may get some ridiculous result. Yeah. All right. Yeah. This version, that's before our limit step. We need to take the limit. Okay. All right. When delta t goes to 0, we take the limit. We get dH over dt equals that expression. That's the exact formula. No approximation. Yeah. That's our second equation. Okay. All right. Next. Now, we have two equations, right? Two equations. This is h prime. This is the h prime function. Okay. Two equations. Then we combine these two equations. Yeah, because this v, we replace the v here by the right-hand side of our first equation. So v is gone. Okay? V is gone. So in this equation, we only have the h function. V is gone. So this ODE is separable. Separable, we know how to solve it. Yeah. Yeah. So finally, we derived a separable ODE. Initial value given, h of 0, the height, initial height, 2.25 meters. And to find a solution, so I put it in further explanation number 3 of 1b. Okay. Okay, module 1 part B. Yeah. Yeah, to save some time. Yeah. Yeah. So that's our problem number 6. Yeah. All right. Yeah. Okay. Yeah. Next, I need to B.3 topic, extended separable ODE. Extended. Yeah. 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 So we want to cover more cases. Yeah. The original separable case still quite limited. Yeah. So we want to do more. Yeah. So here, let's look at the extended method, reduction to separable form. No. All right. So the separable form, this is a typical separable form. Okay? Yeah. But too limited. Yeah. So many equations, if we can only apply our technique on this type of equations, many equations we cannot solve. Okay? Yeah. Yeah. So here we want to consider some new form. Yeah. But a new form has some special structure. So we can take advantage of the special structure to make it separable. Yeah. All right. For example, y prime equals f of y over x. Yeah. So here, inside f function, the structure is y over x. That structure is special. So we can take advantage of that special structure to make this equation. Yeah, this equation, if you view it the first time, it's not separable, right? How can you separate x and y inside the parentheses? Yeah, you cannot separate them. Yeah. But we can convert it to a separable form. Yeah. All right. Look at this example. Yeah. This example, how can you separate y and x? Nobody can separate them directly. Fortunately, the structure is special. Y over x appears inside parentheses. Y over x appears other places. That means this structure is important. It is useful. So we want to take advantage of this special structure to make it separable. All right. Yeah. The function f could be very complicated. Yeah. What's the f function? Yeah. You know, could be very complicated. Yeah. All right. Now we need to use a new variable to represent the special structure. Introduce a new variable, variable substitution. Yeah. So let u be y over x. Yeah. Simple. Yeah. Variable substitution. Yeah. So this function we can write it as f of u. And u is the ratio of y over x. Okay? Then we can write y equals u times x. Then we can take derivative using the product rule, right? Product of u and x. Product rule. Yeah. Yeah. By the product rule of derivative, y prime equals u prime times x plus u. Product rule. All right, now let's go back to the original equation. Yeah. Y prime, we have this new representation, y prime. Okay, all right. Update the form. Yeah. U prime x plus u equals f of u. Yeah, yeah. The form is quite different this time. The good thing is we can separate u and x. We can separate u and x. Yeah. So move u to one side, and the u prime du over dx, right? Du over dx, separate. So this is the separable form. Separable form. Yeah. Yeah. We did a conversion in this way. Yeah. So let's apply this method, extended separable method on that example. Pretty easy. Yeah. So the u, yeah, I mean, yeah, same u. Yeah. All right. After we do the conversion like that, we get du over sine of u equals dx over x. Then you take integral both sides. That's not too hard, right? Yeah. Integral of du over sine u. Yeah. I think it's not too hard. Although at the denominator, but yeah. So you can find it. Yeah. All right. So here, yeah. So after this example, yeah. Yeah. So I may like you to think about slightly different example. Y over x, k times, some k is a constant. Constant. K times x. You can use the same way. Yeah. Yeah. So in my questions, so I may change slightly. Yeah. Yeah. Okay? Yeah. Change slightly. Yeah. So the structure inside parentheses, yeah, it's a ratio. So I want to give you the ratio. Yeah. But the way I write the ratio slightly different from the original ratio. Yeah. Yeah. But I don't want to make it too complicated. Yeah. So after you take derivative, after you do, this kind of manipulation, product rule derivative, you can handle it. Yeah. The bottom line is you can get a nice form after, the similar transformation. Yeah. Yeah. All right. Yeah. So before our break time, I want to give you two simple examples of this method, extended separable ODEs. All right. First example, second example. Okay? Very simple. Yeah. All right. The first example, because if you work on the original equation directly, you may not be able to see how to do the conversion, right? Yeah. Separable. How to make it a separable. Yeah. All right. First, let's write y prime equals some expression, y prime. Yeah. So we get this fraction. Yeah. Second, we write the fraction in this two-term form. Okay. First fraction minus second fraction. Then you can see the ratio clearly, y over x ratio clearly. Yeah. But the x over y, it is just the reciprocal of y over x. Yeah. Related, reciprocal. Yeah. All right. Let us still use variable substitution. U equals y over x. Now we can write y prime, in that way, y prime equals u over 2. 1/2 times u. 1/2 times u. So u over 2. This one, 1/2 times reciprocal of u. 1/2 times reciprocal of u. So you put a u at the denominator. Yeah. So that's a u expression. Separable. Yeah. This one, after simplification, and you can write the separable form in this way. Yeah. You take antiderivative, integral both sides. Pretty easy. Yeah. You can do it easily. Yeah. Yeah. So here I do not need to complete it. Okay? Yeah. 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 Pretty straightforward. Yeah. All right. Second example. Second example, yeah. Also special structure inside parentheses, but it's not a ratio structure. It is not a ratio structure. No. But we can use the same idea. Even if it's not a ratio structure, but our variable substitution method still works. Yeah. So let's try it. Solution, yeah. Let U be the whole expression inside the parenthesis, y plus 4x. Yeah. Then let's take y prime. Yeah. Y prime equals, yeah, that's U, right? Yeah. U prime equals y prime plus 4, so y prime equals u prime minus 4. Yeah. Also very simple. Yeah. Y prime equals u prime minus 4. Yeah. All right. Then y prime equals u squared. Yeah. Equals u squared. Yeah. Some nice separable form, right? Nice separable form. See? Yeah. All right. Then we try to separate du over u squared plus 4 equals dx. Yeah. Then we take integral, you can find the solution easily. Yeah. Okay? Yeah. Yeah. For this class, I only give you these two forms of the questions. Yeah. You only need to solve these two types of extended separable ODEs. Yeah. Yeah. That's enough. Yeah. But I will change the basic structure. One is this ratio, another is some linear function. Yeah. Y plus 4x, it's a linear function of x and y, right? Yeah. Yeah. So these two simple structures, you use variable substitution to convert them to separable ODEs. Yeah. Yeah. For this class. Okay? All right. All right. So let's take a break and come back at 7.